On July 17, 1981, 114 people were killed when two walkways collapsed inside a hotel atrium in Kansas City. It wasn't a freak accident, it wasn't a material defect, it was a design change that nobody bothered to check, approved with a phone call and a rubber stamp. This is how it happened. The Hyatt Regency Kansas City opened in 1980. It was designed to impress. The main feature was a massive atrium, 5 stories tall. And to give guests a view of that atrium from above, the architects designed a series of suspended walkways or skywalks connecting the hotel's tower to the main block at the 2nd and 4th floors. The way these skywalks worked structurally, they hung from the ceiling. Long steel rods, threaded at the ends, dropped down from the roof structure, passed through the box beams of the 4th floor walkway, and continued down to the box beams of the 2nd floor walkway. Box beams, by the way, are just hollow rectangular steel tubes welded together. They look like a box in cross-section. A nut and washer at the bottom of each rod held the walkway up. Original design: 6 rods per walkway, each one running continuously from the ceiling all the way down. Clean, clear load path. The weight of the 2nd floor hangs from the rods, and the weight of the 4th floor hangs from the rods. They're both hanging from the ceiling independently. Simple. That's how it was supposed to work. During construction, the steel fabricator, the company cutting and threading the rods, had a problem. The original design called for rods that were nearly 40 feet long, threaded at both ends, with a precise threaded section in the middle where the 4th floor nut would sit. Threading a 40-foot rod that precisely is difficult, and keeping it from getting damaged during shipping is worse. So the fabricator proposed a change. Instead of one continuous rod from ceiling to 2nd floor, use 2 shorter rods. The upper rod runs from the ceiling to the 4th floor walkway. The lower rod runs from the 4th floor walkway down to the 2nd floor walkway. 2 rods, 1 handoff point at the 4th floor. Sounds reasonable, right? Same number of rods, same connection points, just split in the middle. Here's the problem. In the original design, the nut under the 4th floor box beam carries only one thing: the weight of the 4th floor walkway itself. In the new design, that same nut sitting under the same box beam now has to carry the weight of the 4th floor walkway and the 2nd floor walkway hanging below it. Because the lower rod now attaches to the 4th floor box beam, the entire load from the 2nd floor is now being transferred through that one connection. The load on that nut doubled. Not increased a bit, doubled. And nobody checked whether the connection could handle it. When investigators from the National Bureau of Standards ran the actual calculations after the collapse, here's what they found. The original design, 1 continuous rod, would have met the building code, barely, but it would have met it. The new design, 2 rods, would have failed under dead load alone, meaning even on a day with no people on the walkway at all, just the self-weight of the structure, it would have been at roughly 60% of its capacity. Add a crowd of people leaning on the railings, and you're looking at a connection being loaded to somewhere around twice what it should have been able to handle. The investigators' conclusion was stark. The connection, as built, could handle only about 1/3 of the actual load it was carrying on the night it failed. It hadn't been strong enough since the day they finished building it. What actually happened at 7:05 p.m. is this. The box beam connection on the 4th floor walkway let go. The nut and washer pulled through the bottom of the hollow steel section, and then, in the seconds it took for the 4th floor to fall onto the 2nd floor, the 2nd floor's connections failed too, unable to absorb the impact. survivors described the sound like an explosion, then a cloud of dust, then screaming. The rescue operation lasted 14 hours. People were pinned under concrete in standing water from ruptured pipes. The last survivor pulled out, a man named Mark Williams, had been trapped for over 9 hours, with both legs dislocated, nearly drowning before crews managed to shut off the water supply. So who approved this change? The engineering firm on the project was GCE International. The engineer of record was Jack Gillum. The engineer assigned day-to-day responsibility for the project was Daniel Duncan. The fabricator submitted the new two-rod design as a shop drawing. Shop drawings are a normal part of construction. Contractors propose how they'll build something, and the engineer of records team reviews them for structural adequacy. Duncan reviewed it. He approved it. He later admitted in testimony that he had not performed the load calculations necessary to verify the change was safe. He looked at the drawing. He thought it seemed equivalent to what was designed. He stamped it. In 1984, after a lengthy investigation, a Missouri engineering board found Duncan, Gillum, and GCE International guilty of gross negligence, misconduct, and unprofessional conduct. Duncan and Gillum lost their engineering licenses in Missouri and subsequently in Texas. GCE had its certificate of authority revoked. This was one of the first times in American history that engineers faced the loss of their professional licenses directly as a result of a structural collapse. It set a precedent. Here's the thing about the Hyatt Regency collapse that engineering programs have used as a teaching case for over 40 years. The mistake was not exotic. There was no freak loading condition, no hidden material defect, no earthquake. The failure mode, a connection carrying double the load it was designed for, is about as basic as structural engineering gets. The lesson isn't really about the rod change. It's about what Duncan didn't do when someone handed him a drawing and said, "Is this okay?" He didn't do the math. He trusted that if something looked equivalent, it probably was. In structures, looking equivalent and being equivalent are not the same thing. A design change that seems cosmetic on a drawing can completely reroute how loads travel through a structure. And loads don't care what the drawing looks like, they go where physics sends them. 114 people went to a dance on a Friday night in 1981 and didn't come home. Because an engineer approved a change without running the numbers. That's why when someone hands you a shop drawing and says, "It's basically the same thing," you do the math.